Imagine for a moment a huge project, maybe building a massive skyscraper, reaching way up, or like an intricate bridge over a canyon, or even just designing a home that feels just right. What's the thing that holds it all together? It's communication, isn't it?
Always.
How do you make sure every single detail from the big picture down to the tiniest bolt is perfectly understood by everyone involved? It's a huge challenge.
It really is. As old as building itself,
Yeah.
practically, and so easy for things to get lost in translation.
Exactly. So today we're doing a deep dive into a book that didn't just explain construction. It totally changed how we see it, how we understand it.
Right.
We're talking about Francis D.K. Ching's huge, incredibly important work, Building Construction Illustrated.
A classic, absolutely essential still.
For so many architecture and construction students, finding Ching's book isn't just, learning something new. It's like a light bulb moment, a real aha experience.
Definitely. You hear that all the time.
You're maybe wrestling with these really dense textbooks, all abstract descriptions, trying to build a 3D picture in your head from just words.
Yeah, stuff going.
And then you open Ching, and suddenly these complex connections, loads, layers, things that were buried in text, they're just clear.
Yeah.
Distilled into these amazing hand-drawn illustrations.
Crystal clear. It's like seeing the blueprint for understanding itself.
Yeah. A direct line from the idea to the reality. So our mission today is to explore why. Why did Ching's visual approach have such a massive impact on education, on practice?
Right.
We'll look at how he broke things down from foundations all the way up. We're even going to try some audio illustrations to bring his drawings to life a bit.
That'll be interesting.
And then connect it all back to why clear communication is still so incredibly vital in construction today, maybe even more so. Okay, let's get into it.
Yeah, and it's a great point you make, because even before we dive into the specific details, what's really striking is how his visual method, by actually showing connections, relationships, even forces, it just fosters a deeper understanding.
Systemic, you mean?
Exactly. More systemic than text alone ever could. It stops being about just memorizing parts. You start seeing the whole integrated system, how everything affects everything else.
Which is critical in construction.
Absolutely crucial. Everything's connected.
I can almost picture that student, years ago, maybe frustrated, trying to figure out a column detail or a roof joint from just pages of words. What was the real struggle back then before Ching? Was it just that there weren't enough pictures?
Well, it wasn't just the lack of pictures, though that was part of it. It was the cognitive load, the mental effort required.
Right.
Think about putting together some complicated flat pack furniture, but only using the written instructions. No diagrams.
Oh, nightmare fuel. Yeah.
So you might know what a dowel is, right? But seeing exactly how it fits, how it aligns, how it makes the joint stable, that's a whole different level. Before Ching, translating those text descriptions into a solid mental picture was a real hurdle for a lot of people. A barrier, really.
So you might get the concept of a joist.
Yeah, you might understand the word. But seeing how it's notched, how it sits on a beam, connects to a ledger, how the subfloor goes on top, those are layers of understanding that text just struggles to convey efficiently.
It's bridging that gap, abstract ideal to buildable thing.
Precisely. Tangible reality.
And that's where Ching's genius came in. He brought this incredible clarity, made the invisible visible, the complicated understandable.
Yeah.
His book, Building Construction Illustrated, people always say unsurpassed for clarity and usefulness. It's not just an encyclopedia of wood framing details, although it is that too.
It is very comprehensive. Yeah.
But it's more a teaching tool that speaks this universal language.
Yeah.
Lines, shadows, showing not just what, but how, and even why.
He really did crack the code, in a way.
It transformed education, didn't it? Gave students a kind of shortcut to being well-informed.
It really did. It made abstract stuff tangible almost instantly. Instead of reading paragraphs trying to visualize, a beam to column connection.
Yeah, see it.
You just see it, often from multiple angles in one drawing. So you grasp these complex ideas quickly but properly, without that feeling of being totally overloaded with text.
It taps into how our brains work, right? We
Right.
process visual, spatial stuff much better.
We're wired for it, especially for complex assemblies,
Yeah.
far more efficiently than just reading words about them.
And the style itself, the precise lines, the exploded axonometrics.
The axonometrics.
Maybe explain that quickly. It's not quite perspective, is it?
Right. It's a parallel projection, so no vanishing point. It gives you this accurate, measurable view of all three dimensions at once. They're not just pretty pictures. They're incredibly powerful teaching tools.
Because they show not just the component,
But how it connects, how it functions in the bigger picture, even how it's built, step by step sometimes.
and that clarity just cuts down on ambiguity, which is huge in construction.
Absolutely critical. When you can see every nail, every bolt, every joint, and how it relates to what's next to it, the chance for error just plummets.
So it wasn't just about making it easier to learn.
No, not at all. Think about the consequences of mistakes in construction. They can be costly rework or, much worse, structural failure.
Right.
So reducing that ambiguity through clear visuals is basically fundamental risk management. Ching's work kind of set a new standard for visual detail and documentation. It shifted the expectation. You don't just describe parts anymore. You have to show how they relate and work.
Okay, so with that power of visual communication clear, let's start digging into the building itself, like Chang does, right from the bottom foundations, the unsung heroes holding everything up. How does he make these sort of invisible things understandable?
Well, he shows the logic behind them. Take a footing size. It's not random. It's calculated based on the load coming down from the wall and, crucially, what the soil underneath can actually support its bearing capacity.
Makes sense.
Then he illustrates the vital practical stuff, like damp-proofing and waterproofing. That protective layer, maybe a bituminous coating, maybe something else to stop moisture getting in.
And it's not just the footing itself, is it? It's how it relates to the ground around it.
Exactly. He stresses that foundation walls, especially under wood construction, have to come up at least 6 inches above the finished ground level. And the ground itself needs to slope away, 5% minimum.
Why those specifics?
To manage surface water. Get it away from the building, prevent problems like rot or water pressure building up against the wall. It's simple, but profoundly important prevented design. He makes you see why those details matter.
It's not just holding things up, either. Foundations deal with sideways forces, too, right? Wind, earthquakes.
Absolutely. They transfer those lateral loads into the ground. It works through a combination of friction on the bottom of the footing and what's called passive soil pressure, pushing back against the sides of the footing and the foundation walls.
Things you can't see.
Right. But Ching's cross-sections, maybe using phantom lines, would illustrate these unseen forces, showing how the whole system works together to resist movement.
And then there are anchor bolts. Tiny things, but vital for locking the walls down.
And his precision here is key. He doesn't just say, bolt it down. He gives exact specs like half-inch diameter anchor bolts, embedded at least 7 inches into concrete, no more than 6 feet apart, minimum 2 per sill piece, 1 near each end.
Why so specific?
Because it matters. Functionally critical. A bolt placed wrong or not deep enough, it could compromise the whole building under stress. His visual representation leaves zero room for interpretation.
No guesswork.
None. And he doesn't just stick to standard spread footings. He covers piles, too.
For trickier ground conditions.
Yeah, or heavier loads. He explains uncased piles, where they drive a concrete plug with a steel casing, then ram concrete in as they pull the casing out. Pedestal piles, similar, but they flare out the bottom for more bearing area. And micropiles, small diameter, drilled and grouted. Really useful in cities, tight spots, or for strengthening existing foundations because they cause less disruption. He shows you the options.
Okay, moving up. The structural bones, wood, concrete, steel. For wood framing, what does Ching show us?
Again, not just what a beam is, but how it works, how it supports planking or decking, how it gets supported by girders or posts or walls. He notes the flexibility you get with joist framing, the option to leave the underside exposed for aesthetics.
Practical stuff, too.
Yeah, those useful rules of thumb for beam depth, like span divided by 15 for solid wood beams, span divided by 20 for glulam beams. It's practical knowledge made clear visually, instantly actionable.
And concrete slabs. Seems simple, but I bet there's complexity there, too.
Oh, definitely. He gets into things like rib slabs or waffle slabs.
Yeah.
Details the typical slab thickness, maybe 3 to 4.5 inches.
Yeah.
Gives a rule for total depth, span over 24. Shows specific rib widths, like 5 or 6 inches.
Dome forms.
Right, those square metal or fiberglass forms used to create the voids in waffle slabs. He explains how they come in standard sizes, creating modular systems like 19-inch domes plus 5-inch ribs gives you a 2-foot module.
Clever.
And he highlights the need for solid sections, solid heads, around columns for shear strength. Where the slab meets the column is a critical stress point. Got to get that right.
And then the big stuff, structural steel.
Yeah. He shows how steel beams and girders let you create those huge, open, column-free spaces you see in modern buildings. warehouses, open offices.
Oh.
By using long-span plate girders or trusses to carry the main beams, which then carry secondary beams, it distributes the load efficiently. And he shows how metal decking, often with a concrete topping, fits into that frame to create strong, fire-resistant floors. It's all about strength, efficiency, creating flexible space.
Okay, vertical elements now. Walls. They do more than just hold up the roof, right?
Way more. Exterior walls especially. Yes, they carry vertical loads, but they also have to resist wind pushing sideways. Act as shear walls to transfer lateral forces wind, seismic down to the foundation. And they're the main shield against the weather.
So controlling heat, air, sound.
All of it. Heat, air leakage, sound transmission, moisture, water vapor. Plus, building codes dictate fire resistance. It's a multitasking component, and Ching helps visualize all those layers of performance.
What about masonry walls? Brick and block?
He clarifies things like reinforced masonry. That's masonry with steel bars added inside in joints or cavities filled with grout. Makes it much stronger vertically and much more resistant to buckling or lateral forces.
The bond is key, you said.
Crucial between the steel, the grout, and the masonry units. He also shows composite masonry using different types of masonry in layers or wives, often with a gap, a collar joint filled with mortar, and then metal ties connect these layers.
Little details matter there too.
Absolutely. Things like flashing and weep holes, tiny openings, usually spaced maybe 32 inches apart, that let any moisture that gets inside the wall drain back out. Vital for durability.
And standard wood stud framing, the kind you see in houses everywhere.
He gets right into the nitty-gritty. Corner assembly is why you typically need 3 studs plus blocking there. It's not random. It's to give solid backing for nailing drywall inside and siding outside. Prevents cracks later.
Intersecting walls too.
Same idea. Maybe 4 studs or 3 plus blocking, again for solid nailing surfaces. He even shows specific nailing patterns like 16 VIN nails every 12 inches staggered, and how to fasten the sole plate at the bottom. These details ensure the frame is rigid and the finishes hold up.
What about concrete walls?
He covers those too. Site-cast concrete columns, the complex formwork needed, different surface finishes, and also precast or tilt-up walls, noting how they integrate openings for doors and windows efficiently, different methods for different needs.
Before we move on from walls and interiors, what about drywall and those drop ceilings you see in offices? Do they get the Ching treatment?
They do. He points out that gypsum board, drywall, isn't just a cheap finish. Its real value lies in its fire resistance, and the fact that it's dimensionally stable doesn't shrink or swell much. Crucial for fire safety compartmentation.
And the ceilings.
Acoustical ceilings hide all the messy stuff. Ducts, pipes, wires. But they also provide a neat platform for lights, sprinklers, sound systems. Plus, they add sound absorption and another layer of fire protection for the structure above. He reveals their sort of hidden functional importance.
Okay, here's where it gets really interesting. Moving beyond single parts to how they all fit together. Integrated assemblies, construction sequencing. This is where Ching's visual storytelling really shines, right? Showing how it all becomes a building.
Absolutely. It's like conducting an orchestra. All the parts have to work together in the right order.
It's tough to do this with just audio, but let's try those audio illustrations. Let's bring some of his sequences to life. Starting with roofs, the crown of the building.
Okay. He details rafter spacing, usually 12, 16, or 24 inches apart. That spacing isn't random. It depends on the loads, snow, wind, and what the roof sheathing can span.
And he shows all the parts.
Yet the ridge board at the peak, cripple rafters, headers over openings, valley rafters where roof slopes meet, dormer framing, seeing it all laid out in one of his isometric drawings just makes the whole geometry click. You see the logic.
And waterproofing is critical up there.
Paramount. The roofing membrane, it absolutely must slope at least 1/4 inch per foot. That's a 1.50 ratio to get rainwater to the drains.
How do you get that slope on a flat roof structure?
He shows different ways. You can set the support beams at slightly different heights, or add a layer of tapered lightweight concrete fill, or install tapered boards of rigid foam insulation right on the deck.
Different membrane types, too.
Right. Traditional build-up roofing, multiple layers of asphalt and felt, or newer single-ply membranes. Different methods, but the goal's the same. A watertight seal, get that slope wrong, and you're just asking for leaks.
Insulation and ventilation are part of that system, too.
Definitely. He shows insulation, usually below the roof deck, and crucially, where to put the vapor retarder always on the warm side of the insulation.
Why there specifically?
To stop warm, moist air from inside the building getting into the cold roof assembly and condensing. That condensation causes rot, mold, Big problems. Ventilation, like in an attic space, is also key to manage heat buildup and moisture. It's a whole system working together for longevity and comfort.
Let's look at some specialized assemblies now, things where precision is everything, like passive solar design.
Okay, he illustrates the three main types. Direct gain sunlight comes straight in through windows, heats the space. Indirect gain sun hits a thermal mass, like a thick wall, which stores heat and releases it slowly. And isolated gain, like a sunroom, capturing heat separately, then transferring it.
And controlling it.
Yeah, he shows the mechanisms. Vents, dampers, movable insulation panels, shading devices, how they all work together to manage that solar energy intelligently, not just letting it flood in, but controlling it.
Glazing systems, windows, and glass walls, they seem simple, but aren't.
Not at all. Ching shows the ideal. The glass unit kind of floats in the frame, cushioned by resilient gaskets or tapes, no direct glass-to-frame contact.
Why is that so important?
Thermal movement. Materials expand and contract with temperature changes. If the glass is locked tight in the frame, it'll crack. He details the gaskets for weather seals and those tiny weep holes at the bottom.
Weep hole.
Yeah, essential little drain paths. If any water gets past the outer seals, it can drain out through the weep holes instead of getting trapped and causing damage. The frame itself has to be strong enough to resist wind loads and structural movement without putting stress on the glass. It's a careful balance.
Even everyday doors and windows get this treatment.
Absolutely. He shows the typical framing around openings, headers, sills, jack studs, and stresses filling the gaps between the frame and the rough opening with insulation. Seems obvious, but often missed. Huge for energy efficiency.
Different designs, too.
Yeah. Panel doors, louvered doors, French doors, standard sizes. For windows, details like filtering fins that integrate with the weather barrier, sill extensions that stick out slightly to form a drip edge, kicking water away from the wall below. Small details, big impact on preventing leaks and drafts.
All right, let's try our first audio illustration. Concrete slurry wall construction. Ching's figure 2.18. This is complex underground stuff. Let's paint picture. Step A. Okay, imagine this. At the surface, they install these low, sturdy, temporary concrete walls, guide walls. Then a big clamshell bucket starts digging a deep, narrow trench between these guides. But it's digging through this thick, soupy mix bentonite clay slurry. Here are the machine's hydraulics, the churn of the bucket, and that thick mud.
Step B. The digging goes down, deep. That bentonite slurry is key. Its weight, its fluid pressure pushes outwards and stops the sides of this deep, narrow trench from collapsing in on themselves. So you have this deep channel held open just by this engineered mud. Pretty amazing.
Step C. Next, a huge cage of steel reinforcing bars all welded together is lowered slowly, carefully, down into the slurry-filled trench. You'd hear the clang of steel, the whir of the crane as this heavy rebar cage sinks into the murky liquid.
Step D. Now the concrete. It's poured using a special pipe called a tremie, which goes right to the bottom of the trench. The concrete flows out from the bottom, smoothly filling the trench upwards. As the heavier concrete fills the space, it pushes the lighter bentonite slurry up and out. That slurry gets collected, filtered, and reused. It's a continuous, controlled pour happening deep underground.
Step E. And finally, once the concrete wall section is cured, as they excavate the soil from one side of it, they install tiebacks anchors going back into the earth behind the wall to secure it permanently. The result: a strong, reinforced concrete wall built underground, often used for deep basements or retaining walls in tricky situations. All done with this incredible sequence. Okay, audio illustration number 2. Reinforcing a masonry wall. Section 5.18. Making brick or block walls stronger from the inside.
Right. First, picture placing those steel reinforcing bars vertically, sometimes horizontally too, inside specific cavities or thickened mortar joints within the wall as it's being built. These bars are the hidden muscle.
Then comes the grout.
Yeah, a very fluid mix. Portland cement, aggregate, water is poured into those cavities containing the rebar. It needs to flow easily to fill every nook and cranny completely, embedding the steel.
And the bond is everything.
Absolutely essential. That bond between the steel, the grout, and the masonry units is what creates the composite strength. Ching even specifies details like needing a certain minimum thickness of mortar cover over horizontal joint reinforcement. And he shows different types of ties, like ladder loops, used to connect multiple layers or withes of masonry together, making the whole wall act as one strong unit. It's engineered strength.
And our third audio illustration connects back to foundations. Damp proofing and waterproofing. Section 3.14, keeping water out.
Visualize that protective membrane being applied to the outside of the foundation wall. It has to start 6 inches above the finished ground level and go all the way down, right to the top of the footing. A continuous barrier.
What kind of barrier?
Damp-proofing might be a bituminous coating, like a thick black paint or an acrylic-modified cement. On CMU walls, block walls, he specifies first applying a parge coat, a smooth layer of cement mortar, then the bituminous coating. For true waterproofing, needed for higher water pressure, it's usually thicker membranes, rubberized asphalt, butyl rubber, things that can stretch and bridge small cracks. And sometimes for really tough conditions, they use bentonite clay, either sprayed on as a slurry or applied in panels. The amazing thing about bentonite is it swells up like crazy when it gets wet, forming this dense, practically impermeable barrier. It can even self-heal minor punctures.
Wow.
And connecting this back, the level of detail needed just to describe these steps verbally, it mirrors the precision needed in the actual drawings and specs.
Yeah.
It really underscores that link. Clear communication leads to successful execution. Simple as that.
That's such a critical takeaway. That precision is what bridges theory and practice. Ching's work did that inherently, didn't it? Bridge the gap between a design idea and how you actually build it in the field?
Absolutely. He wasn't just showing abstract shapes. He was illustrating the mechanics of assembly, layer by layer, connection by connection. His drawings became the basis for those construction documents, the CDs or working drawings that builders rely on daily.
I've had stories, maybe apocryphal, of students taking their Ching books onto job sites as rookies, literally using them as reference when the official blueprints were confusing.
I believe it, because his work inherently promotes constructability. That's the term the CMAA, the Construction Management Association of America, uses. It's about how easily, efficiently, and effectively a design can actually be built.
And that depends
On the clarity, consistency, and completeness of the contract documents. Ching's visual clarity is the absolute embodiment of designing for constructability, making sure it's not just buildable in theory, but buildable in reality.
which in turn minimizes errors, because ambiguity in drawings leads to interpretation, guesswork.
And that leads to non-conforming work, as the CMAA calls it. Stuff that doesn't match the documents has to be torn out, redone, costly, time-consuming, frustrating.
Imagine building a complex roof truss from a drawing that isn't clear on a key connection. You make your best guess, it's wrong.
Exactly. Ching's level of detail helps prevent that by making the expected quality level totally unambiguous right from the start.
And it affects bidding too, right?
Yep.
Clearer drawings mean more accurate bids.
Definitely. If drawings are poor, ambiguous, the contractor has to guess, build in extra contingency money, or risk underbidding and losing money later. The owner faces risks too. Ching's thoroughness reduces that risk for everyone, allows for tighter bids, clear expectations, fewer disputes. It builds trust, literally.
So fast forward to today. With all our technology, does this core principle of clarity still hold up? What does it mean for construction now?
Oh, absolutely. Maybe even more so. The whole industry, the AEC culture, is shifting.
How so?
Moving away from the old design, bid, build, low bid wins, command and control style.
Right, adversarial sometimes.
Yeah. Towards more collaborative approaches. Things like construction management at risk, CMAR, design build, integrated project delivery, IPD. The goal now is more about optimized solutions, value, innovation, not just the lowest upfront price.
And that requires a different mindset.
Totally. It demands flexibility, transparency, open communication, real teamwork across disciplines, integrated thinking. It's a big shift.
And that must put a huge emphasis on communication and engaging everyone involved.
Exactly. Stakeholder engagement is key. The PMBOK Guide Project Management Body of Knowledge stresses this, identifying, analyzing, proactively engaging with all stakeholders right from the start.
Not just informing them.
No, building relationships, frequent two-way communication, interactive meetings, informal chats, sharing knowledge, making sure everyone, client to subcontractor, feels heard and is part of the process.
Trust becomes vital then.
Paramount. People need to represent their roles and authority accurately, so everyone understands who can make decisions, commit resources, approve things. Peter Drucker pointed this out. Knowledge work needs extreme clarity on decision authority and clear channels. Otherwise, it's just chaos and delays.
And clear communication is the best way to prevent misunderstandings and disputes.
Absolutely. Simple tools become vital, like shop drawing logs. Shop drawings are the contractor's detailed plans for how they'll build or fabricate something. Keeping track of them, reviewing their status regularly with subs and the design team. It avoids delays and helps pinpoint responsibility if things go wrong, like late equipment delivery. It's a paper trail for clarity.
Subcontractor agreements, too, need to be crystal clear.
Crucial. The scope of work needs to be fully understood by everyone. Subs need to confirm their price covers the work shown in the latest drawings. Using detailed interview forms during negotiation helps document everything, heading off disputes later.
And change orders. They happen on every project.
Always. The key, as CMAA points out, is having specific, documented procedures for initiating and approving them, led by the construction manager usually. Again, it all comes back to clear, documented, agreed-upon communication.
Which brings us to technology. How is it enhancing this clarity? BIM, building information modeling, seems huge here.
It is. BIM is way beyond traditional 2D CAD. It's 3D parametric modeling. Meaning components in the model have data attached. They know what they are and how they relate to other things. This makes designing easier, editing faster, and dramatically reduces coordination errors because the model understands the relationships.
And visualization.
It's a fantastic tool for just seeing the design. Plus, it supports all kinds of analysis, structural energy use, daylighting, and clash detection.
Finding where things collide.
Exactly.
No.
Automatically searching for intersecting volumes, like a pipe hitting a beam. You find these problems in the model before they happen on site. You can even combine models from different disciplines, structure, plumbing, electrical, to check everything together.
And 4D and 5D.
4D links the 3D model to the construction schedule, so you can visually simulate the construction sequence over time, watch the building go up virtually. 5D adds cost data to the model elements, allowing for dynamic quantity takeoffs and real-time cost feedback during design. It's a powerful, integrated information hub.
So BIM is basically Ching's clarity on steroids.
In many ways, yes. But challenges remain. Interoperability is still an issue.
Meaning getting different software to talk to each other.
Right. Keibert notes this partial disconnect. Data exported from one BIM tool might not be fully compatible for, say, energy simulation in another specialized tool. Standards like IFCs and GBXML help, but we still need more seamless data transfer. The communication problem persists, even digitally.
But on-site, technology is making a difference. Tablets, for instance.
Huge difference. Giving field staff instant access to everything: drawings, reports, RFIs, communications, punch lists, safety checklists, contracts, right there on a tablet. No more lugging rolls of drawings or digging through files. Information right where it's needed, when it's needed. That's empowering clarity, just like Ching did.
And this focus on clarity runs through project management fundamentals too, like risk and quality.
Absolutely. CMAA stresses having a uniform cost estimating framework throughout the project lifecycle for consistent reporting, establishing clear baselines, approved versions of plans or budgets to measure actual performance against, constant clear communication of expected versus actual.
Schedule management too, keeping track of complex timelines.
Yeah, schedules are always changing. Methods like CPM, critical path method, or PERT help manage task durations and dependencies. For repetitive work like floors on a high-rise, linear scheduling, or line of balance visually track progress, communicating the schedule and any changes clearly to everyone is vital.
And safety, probably the most critical area for clear communication.
Without a doubt. CMs monitor contractor safety. Before any high-risk work, the contractor must do a job hazard analysis, a JHA, that gets discussed in safety meetings, communicating safety rules and procedures clearly, unambiguously, to every single person on site paramount. There's no room for misunderstanding when lives are at stake.
Which, I guess, brings up that question. We have all these amazing tools, sophisticated methods, awareness of best practices. So why do communication breakdowns still happen so often? And how does that bring us back to the kind of fundamental clarity Ching achieved with just pen and ink?
That's a perfect question to reflect on as we wrap up. It really does bring us full circle. So to recap, we started by thinking about just how complex construction is and how Francis Ching's Building Construction Illustrated just cut through that complexity with its incredible visual clarity. We journeyed from foundations through structure, walls, roofs, all the way to integrated assemblies and sequencing. We even tried to audio illustrate some of those step-by-step processes, trying to capture the precision he put on paper. His legacy, yeah, it's mainly in the drawings, but it speaks volumes about how absolutely essential clear, unambiguous communication is. Whether it's a tiny footing detail, a major steel connection, or how waterproofing layers overlap. Precision in conveying information is just everything.
He showed that a picture really can be worth 1,000 words, especially if those words might be misunderstood.
Or just fail to capture those crucial 3D relationships.
And these principles are, if anything, even more relevant today, wouldn't you say? With our complex teams, BIM, collaborative delivery, the need for clarity has only grown.
Absolutely intensified. From engaging stakeholders to writing clear contracts, managing risk and quality, everything hinges on shared understanding, the very principle Ching embodied with every line he drew.
He showed us that great design isn't just elegant, it's fundamentally comprehensible, easy to understand, easy to build correctly. So here's the final thought for you to mull over. As technology keeps racing ahead, more sophisticated models, AI, real-time data, what new visual languages, what new ways of communicating will emerge? How can we maintain or maybe even surpass the kind of clarity Ching achieved, ensuring no detail gets lost, even as projects get exponentially more complex? It's a challenge for everyone in the industry as we build the future. How do we ensure clarity remains the ultimate foundation?